Okay, so we're going to do an example now where we utilize the Modi's method to find the optimal. So we've already set up the initial tableau which using the northwest corner method, and from this point onwards we're going to utilize Modi's method. So a reminder that Modi has a couple steps to go across. The first one is to find your rows and column numbers using your cost coefficients. The second one is once you find your rows and column numbers, you find your difference values, and that also uses your coefficients and the rows and column numbers that you create. Then it is going to be investigating those difference numbers because they have an impact on your objective function. Then it'll be if the difference is, if there's one that is negative, in other words, it's going to decrease your objective function, you bring that one in, and then you look at the loop system. And after looking at the loop system, you would change your decision variables. In other words, you also end up switching the non-empty cells and the empty cells. You'll switch one of them basically. And then you follow the process again of checking your rows and column numbers, finding your rows and column numbers, looking at your difference values to investigate if it's optimal or not. So we're going to go through that whole process. So the first thing we're going to do is just discuss how we get our rows and column numbers. So remember, we have the formula Cij is equal to Ri plus Kj, and we're going to use this to work out our row and column numbers with setting, our row as the subject of the formula. So we have Ri is equal to Cij minus Kj, and also looking at the case where our column number is the subject of the formula. So we have Cij minus Ri. Now you have to first let your row number or your column number, one of your row numbers, one of your column numbers, to be equal to 0 so that you can just move on, kind of a thing. So in this module, we always set R1 equal to 0 because it just makes sense. It's like a quick little fix. So we have that R1 is equal to 0. And the moment we do that, we now have an equation where we have only one unknown, because here we now have, the cost and a row value, which means we can work out the column value. So the reason why we do that is obviously so we can start the entire process. So in this case, we can now go ahead and work out K1, and K1 is basically the cost minus the row, which is 5 minus 0, which is 5. And you will do this for all the non-empty cells. So wherever there's values, you're going to use the cost function and work out the row and column values. So it's connected to the non-empty cells, is connected to your basic variables. Okay, so we're going to go ahead and do the rest of them. So here we have the column number and we have the cost, so we can work out the row number. So just be careful, like you'll always use the row that's, the row it's in and the column it's in, and you'll need to investigate and find ones where you only have one unknown. So sometimes it's not going to follow the correct order. You won't go solve for K1, K2, K3, and then for row 2, row 3. You will mix it around depending on, whichever formula has only one unknown. So in this case, we have the cost, we have the column, so we can work out the row. So we can go 8 minus 5, and that's going to give us our row number. So that is going to give us R2 is equal to 3. Then we're going to move on and look at non-empty cells again. So here we have 4. We don't have the column, but we do have the row, so we can work out the column. If we had to look at this one over here, instead, we have 7, which is the cost. We don't have the column number, and we don't have the row number. So we can't solve this one yet. Again, here we have, the row and the cost, so we can work out the column number. So we have 4 minus 3, that gives us 1. So K2 is equal to 1. Now we have this column number, we can use that cost to work out that one's row. So now we have a situation where this block has 2 knowns and only 1 unknown attached to it. So we have 7 minus 1, and that's going to give us 6. Okay, now we do the last block, and we have the cost there is 5, and we have the row, which is 6, so we can work out the column. So 5 minus 6, that's going to give us K3 is equal to minus 1. So step 1 is done. We have the rows and we have the columns. Now we get to work out the difference. So the difference is the this formula here where you have your cost minus your row number plus your column number, which is also Cij minus Ri minus Kj. And you can also rewrite this in a different order of Cij is minus Kj minus Ri. So, you know, you can switch this part up. It's not going to be a big deal in order. Now you will do the differences for every empty cell, because the differences is going to give you an indication on if you had to bring, so remember these are decision variables basically zero. The blocks where they are empty are representing zero decision, the decision variable for that optimal, for that solution, not necessarily for that optimal solution. So the non-basic variables basically. But what you're doing now with this difference is it's going to tell you if you had to increase it from 0 to 1, what is its impact going to be on the objective function? Like, so how much is it going to increase or decrease the objective function? So the differences is literally helping you decide if you want to increase from 0 to a value, which one will be the most beneficial to bring in as a basic variable? In other words, bring in as a non-empty cell. So let's go ahead and work out all our differences. So again, because it's talking about the ones that were 0, so it's the empty cells, we will have to, you know, look at for the differences for all the empty cells. So we have, you know, the cost minus the row minus the column. So we have the cost, which is 4, minus the row, which is 0, minus the column, which is 1, so that's going to give us 3. Then we do it for, you know, the next one. So we have 3 minus 0, that gives us 3. And then minus 1, that gives us 4. And we move on to the next non-empty cell, sorry. So we have 3 minus 3, that gives us 0, minus 1, and that gives us 1. Then we have this block over here. We have 9 minus 6, that gives us 3. 3 minus 5, that gives us minus 2. And now we're at the point where we can actually check whether this current solution is optimal or not using the differences. The differences tell us whether it's optimal or not, because again, that difference is telling us if we had to bring the variables of the empty cells, so make them positive non-zero values, what the impact is going to be on the objective function. So if they were all positive, that means bringing in any of them would actually increase our objective function. And because our problem is to minimize, that means we're already at optimal, because none of those can be brought into our solution and actually minimize our problem for us. But if there are any negative ones, that means we're not at optimal yet. And that's what we're looking at, or what we're looking for. So in this case, we do have a negative one, which means we're not at optimal. And we move on to the next step in our Modi method, which is saying, okay, well, we know it's not optimal. We know that if we bring in this decision variable into our basic variables or our non-empty cells, it's going to decrease our objective function. So we say, okay, we want it in there. We don't know how much we can increase it by yet. So we have that plus. And now we need to remember what is actually happening here. So we want to increase that one, but now we need to consider the impact it's going to have on that constraint and that constraint. So let's just write those constraints down to make it a little bit easier for us. So the column constraint there is x11 plus x21 plus x31 is less than equal to 300. And then we have the row, which is, you know, your x31 plus x32 plus x33 is less than equal to 300. Now we say we want to increase that one basically. But we have 100 and 200 there, so we have this is actually 100 and this is actually 200. And we have 100 and 200 there. So we can see now, if we just look at that equation, if we had to increase this one, if we don't make changes to one of these, so that one or that one, we will not meet our constraint. And the same thing happens here. If we had to increase this one, we would not meet our constraint because that's 100 and that's 200. So what we have to do is we have to think about and implement this of saying, if we increase this one, either this one has to go negative or this one has to go negative. And the same process here. Now, at this moment in time, we don't necessarily know which one is going to be beneficial for us. And the reason why this is going to be a bit of an effort for us is the fact that if we do this, we're going to end up impacting the constraint of whichever one we decrease. So say, for example, that we do actually go through the process and decrease, let's look at this one here, the x11. If we had to decrease the x11, for example, and I'm doing this on purpose because it's not going to work out. If we had to decrease that one, then we're impacting that one's constraint, right? So we're like, fine, that constraint still gets worked out because it balances with, what we're doing there. But the moment we decrease that one, we are changing that constraint. And we're changing that constraint in terms of, we have the x11 plus x12 plus x13, and we have obviously the capacity for them to produce kind of thing. We have that less than or equal to 100, and you're like, that's fine, we can decrease it. But remember, we're also trying to have it staying at optimal. So we want to actually have it on the boundary because optimal occurs at the extreme point. So we technically want more of a situation where that, that equals to situation is occurring. So in this situation, if we decrease, that one, we should be increasing one of those. But currently, those are non-basic variables. They're empty, they are equal to 0. And we don't want to bring in more than one variable when you're going through this process in one round. So we need to look at a case at least where there is a situation of, you can do a plus and minus. You can create that loop that we talk about in the MODI steps. So we need to investigate that. So in this case, the one of choice would be this one here. We would decrease this one. And then we can see, hey, we can immediately impact it with the rest because we can immediately then say, well, whatever we change here, we could increase this one here and, still have the constraint being met at the boundary that equals to point. So we do need to consider that. We need to go through the process of just exploring that option. And again, it's at the boundary. So we have, that plus there. And again, if you just want to see that equation, it's, your 2,1 plus your 2,2 plus your 2,3. And at the boundary, kind of like 300, but you can have the less than or equal to, it's not a big deal. If you subtract that one, that's 0. So, kind of non-existent kind of a situation there. Then you can do the plus. And again, because it's at the boundary, you would want it to be equal to, because it's extreme. The extreme point occurs, where it is meeting that. So something that may not have necessarily been spoken about too much, but wherever we have these, non-empty cells, the constraints involving these non-empty cells are at the most extreme that they can be, because they are making up the corner point. So those ones are, where we talk about it, the inequality is not just being met, it's literally being met at the very end of it, so the boundary point of it. I keep on talking about this, but just like think about that idea of, say you had, a bunch of different constraints, and now you have this point x and y, right? And technically you also had a constraint here, a non-negativity constraint and a non-negativity constraint. When we're referring to the basic variables or the non-empty variables here, kind of thing, you would, I know it's in 2-dimension, it's not going to be the most accurate representation, but what we're basically saying is this constraint is active and this constraint is active and binding. And that means that at this very point, where it's equal, it's where it's that straight line aspect of it, and not necessarily everything like below it kind of a situation or above it. So it is a binding constraint. Let's just keep that in mind and bear that in mind. Okay, so we have the plus there, and then we have to once again go, well, that if that is increased, it now affects that constraint. So we need to find out, obviously, which one of these can we change? In this case, there's only one that we can change, so we have that minus. And now we have a loop occurring. And you'll always have some sort of loop, because obviously it needs to all balance out. So that's what when we talk about the loop, that's what we're talking about. Now we have the loop. Now we can figure out how much we actually have to play with to increase this by. And when we're looking at that, because we increase in it, we have the plus. We have to look at what is available to subtract, because the subtract is, keeping that constraint being met. So if we have to look at this for what we have available to subtract, we have 200 over here, and we have 100 over here. But remember, it must all balance out and the constraints need to be met. So we choose the smaller one. And again, that's because, again, if we look at this process, so we have, we don't do this one here, we have this one, right? And then we have this one. So that's the ones that we're looking at. If we had to choose the 200 instead, we'd have to subtract 200 from both of them. We don't have that to subtract, in the process there, because it's not going to then work out to be on the boundary point. We only have 100 to play around with. So just be very, very careful about that. We choose the smallest of them because we only have that 100 to play around with when we switching everything out. We are not utilizing the value from here. We are only utilizing the value from one of those points. Okay, so we utilize the 100. So we add 100 to this one. We subtract 100 here. We subtract 100 here. And we add 100 here. And that's going to give us a new table. So let's just write that in a new table. So what's going to happen? We have, again, that's going to be 100. 100 minus 100 is going to give you 0. So that one's going to become the empty cell. That's going to be 200. That's going to be 100. That's going to be 200. And that's going to be 100. And now you have a fresh new table to do the process all over with. And no matter what, you will do this process over until all your D values, your difference values, are positive. So you're always going to have to, even when you have a fresh new table, go at least to the difference step to investigate whether it's optimal or not. So let's go ahead through the approach again. And this time I'm going to do it a little bit quicker so you can see it's not like super hectically long if you get used to the process. So we need to find our rows and our columns. So we go, okay, that is R1 is equal to 0. That's our standard situation. Then we move on from there. We say cost minus the row, 5 minus 0. That's going to give us K1 is equal to 5. So you're going to notice that pretty much stays the same. What is going to change, what we're going to see now, is that this one's going to change. So wherever a non-empty cell became an empty cell, the rows and columns connected to it may alter. So those are the ones that are going to alter in each like round of the iterations. Okay, so we're going to move on, and now we're going to look at our row value, and you'll notice here it's going to stay the same because you're going to have 8 minus 5, and that's going to give us our 3. Okay, now we can go on to this one here, and we have 4 minus 3, that's going to give us K2 is equal to 1. And you're going to be like, oh, but she just literally told us that the rows and columns there may change. Not necessarily both of them, but you're going to notice, there could be a change in the rest of them. Okay, so now if we look here, we have a situation of we need to find this one, and currently this is unknown and that's unknown. So if we look here, and this is where the row number is going to change, because previously, how did we work out this row number? We worked out this row number by utilizing the 7 minus the 1. But now we don't have this block anymore, and that's why that one changes. So we're now using, obviously the other block. So we have 9 minus 5 is going to give us 4. So we have a new row number because of the fact that this block is no longer, non-empty. And now we can work out this one. And obviously this one's column is going to impact because we use this row to work out this column value. So now we have 5 minus 4, and that gives us K3 equal to 1. Okay, so now we have our rows and our column values. We can move on to find our differences. So remember, our differences is the cost minus the row minus the column. So it's 4 minus 0 minus 1, that gives us 3. Then we have 3 minus 0 minus 1, that gives us 2. Now we have 3 minus 1, that gives us minus 1. And we're already at the point where we're like, oh, it's not at optimal because we have a negative difference. Then we go 7 minus 4 minus 1. So 7 minus 4 gives you 3, 3 minus 1 gives you 2. So at this moment we check, is it optimal? It's not, because there's a difference which is negative, which means we have to go through the process, of bringing this one in as a non-empty cell, as a basic variable, and then going through finding our loop. So again, this is going to be, this one here is going to be a bit easy for us to notice because we have the minus happening there. And then we need to look at, if that's negative, which ones can we impact here? This one happens to just be the plus. And remember, we need to create the closed loop. So we know we're not going to use that one. So we can immediately, have that one as negative. So we have that loop, forming. Right. Now we have the loop forming. We can look at the negatives and choose the smallest negative to put it in there. So we have 100 and 200. We choose the 100 again so that we can meet those constraints. So we have 100 that we're going to add there, and then we subtract it there, we add it there, and subtract it there, and we get a new table. So you see, the first one seemed like it took forever, but once you learn your practice and go through the, the rounds, it gets a little bit faster to handle. So now we have, our new table. And let's just write our new table down. So this becomes the empty cell because, well, no, I lie. That becomes the empty cell because we have 100 minus 100. So we're no longer going to have that one. So let's just put in that one because nothing changed there. Nothing changed there. That one became empty because we have 100 minus 100. Then we have this one is 200. This is 100. And this is 100. Okay, so we have our new table. And now that we have our new table, we go through the process again. So we find our rows and columns to work out our differences. So let's start with our rows and columns. And again, you have that R1 is equal to 0. And we move on from there. Now you'll notice again that this K1 is still 5 because nothing really changed for it. We're still using the 5 there and we're still using the 0 there. So that's going to be K1 is equal to 5. Now we have to move on, and previously we utilized, this block over here to work out our row value. But because this one, is gone, there's going to be an impact now, obviously, on our row value. So we have to, move on from there. So which one can we look at? We can look at this one though. So we can be like, okay, well, we have 9 minus 5, and that's going to give us R3 is equal to 4. Then we have to, again, the whole process is we're looking for the ones where there's only one unknown. So we have the row, we have the cost, we can work out this one's column value. So we have 5 minus 4, and that is going to give us 1. Now you'll notice it's the same as what we did previously. So we're good on that front as well. Now we have this column value, we can work out this row value. Because now we can say 3 minus 1, and that gives us R2 is equal to 2. So you see this row value is the one that changed, which means now when you work out, this column value here is obviously going to be different as well. So we're going to have 4 minus 2 gives us 2. So you would have seen, if you in this one, we utilize that to work out our row value there. And then obviously that has an impact on wherever we utilize that row value to work out our columns. So just be careful about that. You don't have to think about it. You can just do the row and column calculations from scratch. If you want to be a bit more lazy, you actually have to figure out, which ones change and which ones don't change, and work those ones out only. There is a pattern to it, so you can learn to practice it, but at the moment I would just suggest doing your rows and columns just from scratch. Okay, now once again we work out the differences. So we have 4 minus 0 minus 2, that gives us 2. We have 3 minus 0 minus 1, that gives us 2. We have 8 minus 2 minus 5, that gives us 1. And then we have 7 minus 4 minus 2, that gives us 1. And now we're super happy because all of our differences are positive, which means we at the optimal for the minimization problem. So now we can say, that we have an optimal. The optimal is basically x11 is equal to 100, x22 is equal to 200, x23 is equal to 100, x31 is equal to 200, x33 is equal to 100. So those are all our basic variables, our non-empty cells are basic variables, and then all of these are equal to 0. So then we have, x12 is equal to 0, x13 is equal to 0, x21 is equal to 0, and x232 is equal to 0. And that is going to give us, our objective function value, and now we can actually go ahead and work this out. Remember, we take these values and we multiply them by our cost, because remember, our objective function is basically the summation of our cost multiplied by a decision variable, all added together. So it's the summation of these here. So when you work out objective function value, we can read it straight off here. We can say 100 times 5 plus 200 times 4 plus 100 times 3 plus 200 times 9 plus 100 times 5. So you only really have to care about these because those are all zeros. So when you write it down and work it out, you can just look at those if you want to. 100 times 5 plus 200 times 4 plus 100 times 3 plus 200 times 9 plus 100 times 5. Let me just get my calculator out. To work this out, we have 500 plus 800 plus 300 plus 1,800 plus 500, and that gives us 3900. So we have the optimal, with the 3,900 situation, and then we're done.